Okay, good afternoon, everyone. We'll continue from where we left off last time. So, we have started the chapter on stress, and we have started the discussion which would ultimately lead towards the derivation of the Cauchy's law. So, last time I mentioned that in general you are going to have three different planes. In general, you are going to have three different planes, and those would be parallel or perpendicular to the x-axis, the y-axis, and the z-axis. But in addition to that, we would also consider a general plane passing through that point. Okay, so the picture was something like this. So and as you can see, this is a fairly complicated looking thing, but if this was not good enough, they all coincide at this point. We said that we'll consider a plane which was like this, which was additionally passing through this point. So they're all passing through the same point. Now, we don't want to keep it like this. We want to actually utilize this idea towards going towards the Cauchy's law. So what we'll do is we'll consider the axis like this. Okay, we'll draw this again. So this is the x-axis. This is the x-axis, this is the y-axis and z-axis. Now, we'll consider the three planes in general like this. This is one plane. I am not drawing the rest of it because now I want to start clearing up the picture. Okay, so this is the plane which is within the xy plane. Next, we have this. This is another plane which is within the yz plane, maybe something like this. And finally, in the xz plane, we are going to have something like this. Now, if I were to draw this particular plane, which is this arbitrary plane passing through this point, I would have to draw it passing through this point. Okay, please note that this point is this point. I have chosen it to be the origin. Okay, but I don't want to do that. So this is where the genius of Cauchy comes into the picture. So what he did was he said that I will not make it pass through that point. Rather, I will take it at a certain distance away from it. Okay, at a certain distance away from it, such that when that arbitrary plane cuts with these three different axes together with these three already existing planes, it will give me what will look like a tetrahedron. Okay, so let me draw that with a separate color. So imagine that Cauchy is drawing this plane. Okay, Cauchy is drawing this plane not through this point but like this. Okay, obliquely, and wherever it is cutting these three different planes, we are just separating it out. Okay, we are not drawing the rest of it. So it will look like this. Okay, very carefully we have drawn this plane. Okay, so if you consider now this particular diagram, this one, this plane of course, but together with this side, together with this side, and together with this side. Okay, this side. So how many sides are there? There are 4 sides. Okay, it's not a trick question. There are 4 sides. Now, using this, so this is a tetrahedron. Okay, this looks like a pyramid. Now, what we'll do is, we are going to consider the traction vectors on each of these planes, or on each of the sides of this tetrahedron. Because this is an arbitrary plane, we are going to first depict the general traction vector on this particular thing, as well as the unit outward normal. So the unit outward, see, this is a 2-dimensional thing, okay? So I have my limitations also in terms of drawing, but please understand that when I draw something like this, I very much mean that this is perpendicular here, okay? So it is perpendicular to this plane. I will also name it. So this is O, this is A, this is B, this is C. Okay, so this triangle OABC, this is our, this tetrahedron is our OABC. Now over here, I'm going to have this traction vector. Let's say I draw it like this. This is my traction vector. This is my unit outward normal to the plane. So this green colored thing that I have just drawn, this is the traction vector on the arbitrary plane. This is on which plane? This is on the ABC plane. Right? Now, you consider what is going to happen on the triangle OCB. Let me erase this. Okay, so I will separately draw it. So please try to understand that this is the same thing that I have drawn, which was here. That's the same thing. Now, what I will consider is the traction vector which is lying on that other side. Okay, not on this side, because this is the inside of the tetrahedron. I want to depict the traction vector on the outside of the tetrahedron. So on that outside, please do not draw this, okay? What I'm just going to show very lightly, I'm going to have some arbitrary traction vector like this. Okay, please don't draw this. Okay, that will be the traction vector on that OCB plane. Now, if I take the components of it, what do you think those will be? So remember, one of the earliest things which we discussed over in this chapter is that if you take a cutting plane which is perpendicular to the x-axis or parallel to the YZ plane, then on that the traction vector we obtain, if you take the components of it, what will be the components? Just go back and look at it. Exactly, sigma xx, tau yx and tau zx. Okay, or rather tau xy and tau xz. So we'll depict those things. Now you have to be a little bit careful here. Please note that my sigma xx will be opposite to the direction of x, because the unit outward normal is along the minus x direction. So this is my sigma xx. The unit outward normal, again I am repeating, the unit outward normal will be along the minus x. Okay. Now you tell me with all your knowledge, what will be the direction of the tau xy? Exactly, it will be downward. Very good. So this will be my tau xy. And what will be the direction of the tau xz? Along the positive or negative z axis? Negative z axis. In a similar fashion, I will now consider the triangle OAC. So this is OCA or OAC. Here, the unit outward normal is along which direction? Minus y. Very good. So the components, this first component will be what? This is sigma yy. Negative to the x direction, what will I have? Tau yx. Very good. And negative to the z direction, what will I have? Tau yz. Very good. Okay. Next, I will consider the triangle OAB. Here, the unit outward normal will be along what? Minus z. So, this is my sigma zz. Then along minus y, what will I have? Tau yz. Sorry, tau zy. And finally, along negative x, what will I have? Tau zx. Okay. So already it is looking quite cluttered. Imagine what would have happened if I had drawn it on this same diagram. Okay. Now this is a very, very standard diagram. What is the motivation here? Where are we going with this? What we want to do now is to do some kind of a force balance. Okay. Why force balance? You see, here all the things that we have, this one is in terms of the traction. These are in terms of the stress components. But when we want to write force balance, we have to multiply with the areas. Okay, we have to multiply with the areas. Only then we will be able to write the force balance. We cannot write the balance of directly the stress components. Okay. So we have to be very, very careful with the directions now. Now, this traction vector T, it has components Txx, okay? So like that Tx component, Ty component, Tz component, all those things. Now, suppose I want to write the force balance in the x direction. Force balance in the x direction. Okay. Which component of this T vector will I take? Tx. Okay, it has only 3 components, right? Tx, Ty, Tz. If I choose to decompose along the 3 Cartesian coordinate axes. But just taking the Tx doesn't give me the force. I have to multiply the traction vector component with the corresponding area on which it is acting. Okay, so which is the area? No, Tx is acting on which area? ABC. ABC is the corresponding area, okay? So see, this T, it is only acting on this ABC plane, okay? This is the force. This is the force due to the traction vector T in the x direction. Now, you tell me what is the contribution from the sigma xx. See, what are we doing? You just try to imagine, okay? This is a tetrahedron, okay? This is a body, okay? We have not directly written the free body diagram of this, because a free body diagram would entail writing the forces. Rather, what we have done is we have detailed out all the stress components. But when we write the force equilibrium equation, we have to write it in terms of the force. That's what we are doing. We are just multiplying the different stress components with the corresponding areas. That's all that we are doing. Okay. So sigma xx, what will I multiply it with? Triangle OCB. But you note that this sigma xx is in the negative x direction. Okay. So this will be minus. Minus, or I can take it to the right hand side. So sigma xx triangle OCB. Next, do you think that on this triangle OCB there is any other stress component which is contributing in the x direction? No. These components are there, but for the force equilibrium in the x direction, I don't need to take them into account because they are not in the x direction. Next, for this one, triangle OCA, which is the one in the x direction? Tau yx. Okay. Tau yx. Triangle OCA. This tau yz and the sigma yy, they are not contributing in the x direction. Okay, so we are not writing in the force equilibrium along the x direction. Next, for the triangle OAB or OBA, which is the stress component which is contributing? Tau zx. Okay. Now, we just have to do one small trick, which is familiar to you from your vector algebra, which you learned in your 11 and 12, but maybe not quite in the form that I'm going to write it, but just keep an open mind, it will be clear. So see, suppose, so I'm going to the rough column here. Suppose you have a triangle like this. Forget about that picture, okay? This is a generic triangle. Okay, let's say that this is OPQ. Okay, what is the projection of the side PQ? What is the projection of the side PQ? Suppose I have my x-axis like this and my y-axis like this. What is the projection of the PQ along a plane on which, so I'm deliberately trying to complicate it. What is the projection of the side PQ on a plane which is perpendicular to the x-axis? I am repeating my question. PQ side, what is the projection of PQ on a plane which is perpendicular to the x-axis? OP. As simple as that, okay? OP. Alright, so suppose this is theta. Then OP will be what? OP is equal to PQ divided by sin theta. Okay. Sorry, PQ sin theta. PQ sin theta. PQ sin theta. Okay. So OP is equal to PQ sin theta. And OQ is equal to PQ cos theta. But since we are talking in terms of projections, okay, we can rewrite this sin theta and cos theta in terms of the direction cosines. Okay, you don't think like that when you are doing 2D geometry, but it is a special case of that. This sin theta and cos theta are the direction cosines. So we'll now try to think in that fashion again. You consider this triangle ABC. What is the projection of this triangle on a plane? Okay, what is the projection of this triangle ABC on a plane which is perpendicular to the x-axis? It is nothing but this triangle itself, this OCB. Okay, Okay, this is the OCB. I mean, we have written OCB, right? Let's be consistent with that. Okay, triangle OCB. So what will I write here is that this sigma XX will be triangle ABC times, right? So that is the nothing but the direction cosine. Okay, so and that is nothing but the x component of the of this unit vector. Okay, this unit vector. Okay, this unit vector will have the components nx, ny, and nz. Right? This nx, ny, and nz are what? These are the direction cosines of this plane only. Is it not? ठीक है. So if you agree with this, then the rest of it is absolutely easy. Tell me what this triangle OCA is. This will be ABC times what? Triangle ABC times NY. Very good. And triangle OBA is triangle ABC times NZ. Now you see, on the left hand side I have triangle ABC, and on the right hand side I have triangle ABC in each of the terms. Okay, so this triangle ABC is common, so it goes away, and what we are left with is this thing. Tx is equal to sigma xx nx plus tau yx ny plus tau zx nz. All right, please be very careful not to write this as tau xy and tau xz. I know that from basic engineering mechanics, you know that tau xy is equal to tau yx and tau xz is equal to tau zx. But for now, please don't use that. We'll use that later. Okay, but please write it like this. Now, in a similar fashion, if we write the sigma fy equal to 0, what are we going to get? I'll directly write it down. So sigma fy equal to 0, that will give us ty is equal to tau xy nx plus sigma yy ny plus tau zy nz. And finally, if we do sigma fz equal to 0, it will give us tz is equal to tau xz nx plus tau yz ny plus sigma zz nz. That's it. Okay. Now this thing which you have just learned, okay, it is not just limited to some ordinary basic version that I'm giving in the second year level. Even if you go on to do your PhD, these relations will be valid. Okay, this is absolutely general. Okay, no problem. Now you see there is a very nice arrangement that we have come up with here. Okay, these three equations can actually be written in the matrix form. Okay, in a very nice matrix form it can be written. That's what we are going to do. Rohit, this is visible, right, at the side? Okay. So please ensure that this matrix form that I have just written, it is the exact equivalent of these three equations. Okay, please convince yourself this. Okay, now the moment we can write this in matrix form, the entire power of linear algebra is at our disposal. Okay, so you'll see the nice things that are going to happen now. Please note that this tx, ty, tz are what? These are the Cartesian components of the t vector. So can I not write it in short like this? So this t vector is the vector itself, and this square bracket around it means that this is the matrix representation of the vector. Now, who can tell me what this thing is? It is sigma something. What is sigma something? Sigma tilde tilde with a square bracket around it. But is it the sigma? It is the transpose of the sigma. So please go back to your notes from last week where I showed that the sigma is actually the transpose of this. Okay. Here the rows and columns are interchanged. That is the only trouble. Okay. So what we are going to write is that this is the sigma, the stress tensor. This is the matrix representation of it, and this is the transpose. And finally, this n hat, this nx, ny, and nz are nothing but the Cartesian components of the unit outward normal, that n hat. So the entire information which we have done through all these discussions, starting from the beginning of this class, this can be encapsulated in this very, very pretty formula. And this pretty formula is extremely important, and this is the Cauchy's law. Okay. So please do not forget this. In many of our undergraduate textbooks, this thing is not highlighted. But I think this is the root of many of the later discussions, so we must know this. Okay. All right. So what we'll do now is to actually make use of your knowledge of linear algebra time and again. Okay. So it's not the hi-fi thing, very basic kinds of things. The first thing that we are going to look at is, see, what we have managed to do here. We have managed to find a connection between the traction vector and the stress components as they are with reference to the Cartesian coordinate system. Okay, those things, those sigma xx, tau yx, tau zx, all those 9 things that are there, they are there because we have chosen to work with the Cartesian coordinate system. Okay, so it is giving us a connection. Now what we'll do is, we will stay on this plane. We'll stay on this plane itself, and earlier what we had done was, we had taken the components of this t vector along the x, y, and z. But as I had earlier told you last week, that it is also possible that we decompose the traction vector not along x, y, z, rather along the unit outward normal itself and along a direction which is within the plane perpendicular to the n hat. Okay, so that is what I am interested in, and you will see why I am interested in that. So very quickly I will write something, and it gives us a very, very beautiful formula. So what I'm interested in is this TNN. TNN is what? TNN is the component of the T vector along the unit outward normal itself. Okay. So who can tell me what TNN is in terms of the T vector? Tell me. T dot n. Okay. It is nothing but T dot n. Okay, but this is not in the matrix form. I want to have it in the matrix form. So who can tell me what is this in the matrix form? Yes. Suppose I have two vectors. Okay. A vector and B vector. A is AX. So again, so very quick, this is rough column. So A is AX I hat plus ay j hat, and B is bx I hat plus by j hat. Now you know that A dot B is equal to ax bx plus ay by. No problem here, but I don't want to write that. I want to write that in terms of the matrix. What is it? Is this correct? Is this correct? You can't even multiply. Okay. Matrix multiplication cannot be done like this. The number of columns of the first should match with the number of rows of the second. So what is missing? So you need to have a transpose here. Okay. Now because there is a scalar, you could easily have written B transpose A also. That would have been perfectly same. Okay, but I'm choosing to write like this. Now if that is what you understand, what is it here? Makes sense? Okay. Same thing. T is A and N is B. But on that side, I already have an expression for my T. So can I not now write the T and N in terms of the sigma and the N? I can. So let me do that step by step. So this is sigma transpose N. What is this? This is just the T vector. This entire thing has a transpose over it. Right? Okay. Now you tell me, in general, you have some matrix here and some matrix here. Okay. So it is A matrix multiplied with B matrix, and you have a transpose over it. What is the result of that? B transpose A transpose. Okay. So sigma transpose of that. What is that? Sigma itself. Right? So this is the formula that I was interested in. Now you tell me very quickly, do you recognize this form? Again from linear algebra. I don't know if it's taught nowadays. Yes? What is the name of this form? Diagonal. Acha, first of all, everyone settle down, settle down. Come back to earth, come back to earth. It is not that difficult. So this particular form has the name is the quadratic form. Okay, it is the quadratic form. As simple as that. Okay, because if you multiply it all out together, what is going to happen is that you are going to get terms which involve the nx square, the ny square, and the nx and ny. Okay, all of them are quadratic terms. Okay, so if you multiply them all out. All right, now we don't need to worry about them. Now what we'll do is, all of these things we have done in 3 dimensions. But we have not really unlocked our knowledge in a very explicit form in the 2-dimensional things. So that is what we are going to do next. So in 2 dimensions, what is the implications of all these general formulas? That is what we are going to look at. What is it going to help us with? It is going to help us towards proceeding towards finding out various formulas for what is referred to as the stress transformations. Okay, so let's take a look at that systematically. So the plan is like this. You can write it that we are going to study transformation of stresses. We are going to study transformation of stresses in 2 dimensions. Okay, please don't think that we can't do transformation of stresses in 3 dimensions. We can, but we are choosing not to do it. Okay, baby steps. So we are going to study transformation of stresses in 2 dimensions. All right, full stop. Okay, now you listen to me. Towards that end, what we are going to take up is something, a class of problems or a class of situations which are referred to as plane stress problems. Okay, it is not some kind of arbitrary contrivance that I am coming up with. Okay, this plane stress thing. It is extremely important from a very engineering and practical perspective. You may think that it is only referring to such a small class of problems when I draw the diagram, but no, it has a big significance in many different kinds of engineering situations. Now, what is plane stress? Now, first thing, very important for plane stress is to note the spelling. It is not plane. Memorize it, okay? Okay, cut it out and put it in front of your table. Even I have seen some PhD candidates and even postdocs, they write in their presentations that thing. It is so very irritating. Okay, it makes you look like an illiterate person. I mean, at this level. Okay, so this is plane stress. Now, what is plane stress? What kind of a situation? Well, if you have a thin disc-like geometry, What is a thin disc-like geometry? You have all of it in front of you. Your copy. Close your copy. Close your copy. Yeah, hold it in your hand. Yes, hold it in your hand. That is a plane thin disc. Okay, and that is a canonical example of a plane stress. So, in what sense? Okay, so let us look at a general. This is a general thin disc. Okay, and here the x-axis will be something like this, and the y-axis will be something like this. Okay, within the plane. Now, the special scenario which makes it plane stress, first of all, is the geometry itself. But in addition to that, what you have is the nature of the forces which are acting on it. So, for a plane stress or a situation to be plane stress, you need the forces to be lying within the plane. If you have forces which are lying transverse to the plane, then it is not going to be a plane stress situation. Okay, this is a plane stress situation. Now, I am not going to go into the deep details of this description, because when we study plane stress at an advanced level, we spend like half an hour describing the situation itself. Okay, we're not going to do that, of course, but as a very brief summary, I will tell you that when we have plane stress and you have the x-axis and the y-axis located like this, then what you have for plane stress is all these components are 0. Okay, I am not going to go into the deep details, or in fact I am not going to go into the description of why this is so. Okay, for now you accept my word. All right, so sigma zz is equal to tau xz is equal to tau yz equal to 0. Okay, here I am implicitly assuming that you know that tau xz is equal to tau zx and tau yz is equal to tau zy. I have not proved it here, okay, but I am assuming that you have done your BM properly and you remember something from that. So this is what it is. All right, now why am I making such a big fuss about this? You see, if these things are 0, then over here this is 0, this is 0, this is 0, this is 0, this is 0. Effectively, you have as your non-zero components just these 4 things, and this makes our algebraic manipulations, our physical understanding that much more simple. Okay, it is just to go into that simpler thing that we are taking this. But please, again, I want to repeat this and emphasize this, that it is not only for the sake of convenience that we are studying this plane stress. There are many situations in engineering where this plane stress is the situation in reality. Okay. All right. So the first thing that we are going to do, what we'll do is, so here is where we are going. Within the plane stress condition, we are going to find out an explicit formula for this TNN. Okay, it is going to be a very simple formula, but extremely important, not only for understanding the plane stress condition, but also for doing the kinds of problems that we expect you to be able to do by the end of your second year. Okay, so both from a real perspective as well as an examination perspective, that is going to be important. All right, but before that, let's connect with whatever we have learned till now. We started out, if you remember, in the ancient time of previous week, we started out with the three-dimensional potato. Okay, now this disk that I have drawn, is it not a special case of that three-dimensional potato? It is. Okay, it is a special case of the three-dimensional potato. Now there I took an arbitrary cutting plane. Here also I'll take an arbitrary cutting plane. Okay, so I'll slice it off. So what I'll do is I'll draw a cutting plane which is like this. Now what is this cutting? It is cutting this thing here. Maybe it's not such a great diagram. So this cutting plane is passing through the origin. Okay, it is passing through the origin. So what you have is something like this. Imagine that this is my thin disk. Okay, this is my thin disk. My x-axis and y-axis are like this, and I'm taking my cutting plane and I'm cutting like this. Okay, so this purple colored cutting plane is this cutting plane. Okay, I'm cutting it like this. Now this same diagram, if I take a helicopter and if I arrive here on the top and I look down, okay, I look down into the xy plane, what will I see? Will I not see something like this? First of all, this is my three-dimensional potato or the two-dimensional disk. This cutting plane, what will it look like? It will only look like a line segment, like this. My x-axis and y-axis will look like this. Right? Now earlier, when we were talking about the n hat and the traction vector and all those things, on which plane they were lying on? They were lying on that arbitrary plane. So here also, my arbitrary plane is like this. So my unit outward normal will be along which direction? Perpendicular to this arbitrary cutting plane, and that will be within this plane. This is my n hat. Please convince yourself that this is the correct picture. Okay, please understand that this here is my cutting plane. My unit outward normal is perpendicular to that cutting plane. Okay, so this one. Fine. And where is my traction vector? It is certainly not in general along this n hat. That much I know. Okay, somewhere. It is somewhere, but it is not along this n hat. Now what I'm going to do is, I'm first going to find out this TNN. So refer to this. Oh, by the way, I have to first write my nx and ny. Let's say this angle is theta. Then n hat is what? Nx I hat plus ny j hat. But what is nx? Is it not cos theta? And ny is it not sin theta? So no problem here, which means that my n hat matrix can be written like this. Okay? All right. Now, the stress matrix, what was it? Sigma xx, tau xy, 0. From now on, I am going to use tau xy is equal to tau yx. Okay? I am going to use it. Okay? Taking advantage of your BM. So effectively what I will do for this effective two-dimensional case is to not consider these zeros and consider just this inside part, which are in general not zero. So I am going to consider from now on for my stress matrix just this thing. All right? Okay. Now, if all of that is true, then can I not write like this, that Tnn is equal to this thing? All right? I'm just substituting. Okay? Please do the expansion. Multiply it out. Okay? Multiply it out. Tell me what you get very quickly. You have 20 seconds. Do it. Anyone? Plus right. Okay, all good. This is the correct formula. Now, if you look at Beer and Johnson, they have certainly not mentioned anything regarding traction vector. And since traction vector is not mentioned, the TNN also doesn't exist. Okay, none of these things exist, but this formula exists. Okay, so what have we found out that Beer and Johnson was telling us and we have arrived at separately? Okay, to know more, come back after the break. Stop it.